LPIC 1. Topic 101 System Architecture. Armand Shariarian. Topic 101 System Architecture. 101.1 Determine and configure hardware settings. Introduction. Since the early years of electronic computing, business and personal computer manufacturers have integrated a variety of hardware parts in their machines, which in turn need to be supported by the operating system. That could be overwhelming from the operating system developer's perspective, unless standards for instruction sets and device communication are established by the industry. Similar to the standardized abstraction layer provided by the operating system to an application, these standards make it easier to write and maintain an operating system that is not tied to a specific hardware model. However, the complexity of the integrated underlying hardware sometimes requires adjustments on how resources should be exposed to the operating system, so it can be installed and function correctly. Some of these adjustments can be made even without an installed operating system. Most machines offer a configuration utility that can be executed as the machine is turned on. Until the mid-2000s, the configuration utility was implemented in the BIOS, Basic Input/Output System, the standard for firmware, containing the basic configuration routines found in x86 motherboards. From the end of the first decade of the 2000s, machines based on the x86 architecture started to replace the BIOS with a new implementation called UEFI, Unified Extensible Firmware Interface, which has more sophisticated features for identification, testing, configuration, and firmware upgrades. Despite the change, it is not uncommon to still call the configuration utility BIOS, as both implementations fulfill the same basic purpose. Note: further details on the similarities and differences between BIOS and UEFI will be covered in a later lesson. Device activation. The system configuration utility is presented after pressing a specific key when the computer is turned on. Which key to press varies from manufacturer to manufacturer, but usually it is del or one of the function keys, such as F2 or F12. The key combination to use is often displayed in the Power On screen. In the BIOS setup utility, it is possible to enable and disable integrated peripherals, activate basic error protection and change hardware settings like IRQ, interrupt request, and DMA, direct memory access. Changing these settings is rarely needed on modern machines, but it may be necessary to make adjustments to address specific issues. There are RAM technologies, for example, that are compatible with faster data transfer rates than the default values, so it is recommended to change it to the values specified by the manufacturer. Some CPUs offer features that may not be required for the particular installation and can be deactivated. Disabled features will reduce power consumption and can increase system protection. As CPU features containing known bugs can also be disabled. If the machine is equipped with many storage devices, it is important to define which one has the correct bootloader and should be the first entry in the device boot order. The operating system may not load if the Incorrect device comes first in the BIOS boot verification list. Device inspection in Linux. Once devices are correctly identified, it is up to the operating system to associate the corresponding software components required by them. When a hardware feature is not working as expected, it is important to identify where exactly the problem is happening. When a piece of hardware is not detected by the operating system, it is most likely that the part or the port to which it is connected is defective. When the hardware part is correctly detected, but still does not properly work, there may be a problem on the operating system side. Therefore, one of the first steps when dealing with hardware-related issues is to check if the operating system is properly detecting the device. There are two basic ways to identify hardware resources on a Linux system: to use specialized commands or to read specific files inside special file systems. Commands for inspection. The two essential commands to identify connected devices in a Linux system are LPIC shows all devices currently connected to the PCI, Peripheral Component Interconnect, bus. PCI devices can be either a component attached to the motherboard, like a disk controller, or an expansion card fitted into a PCI slot, like an external graphics card. LPIC lists USB, Universal Serial Bus, devices currently connected to the machine. Although USB devices for almost any imaginable purpose exist, the USB interface is largely used to connect input devices, keyboards, pointing devices and removable storage media. The output of commands LPIC and LPIC consists of a list of all PCI and USB devices identified by the operating system. However, the device may not be fully operational yet, because every hardware part requires a software component to control the corresponding device. This software component is called a kernel module, and it can be part of the official Linux kernel or added separately from other sources. Linux kernel modules related to hardware devices are also called drivers, as in other operating systems. Drivers for Linux, however, are not always supplied by the device's manufacturer. Whilst some manufacturers provide their own binary drivers to be installed separately, many drivers are written by independent developers. Historically, parts that work on Windows, for example, may not have a counterpart kernel module for Linux. Nowadays, Linux-based operating systems have strong hardware support and most devices work effortlessly. Commands directly related to hardware often require root privileges to execute or will only show limited information when executed by a normal user, so it may be necessary to log in as root or to execute the command with sudo. The following output of command LPIC, for example, shows a few identified devices. $LPIC 01:00.0 VGA compatible controller, NVIDIA Corporation GM107 GeForce GTX 750 Ti, Rava 2. 04:02.0 Network Controller, Relink Corp RT2561/RT61802.11 GPCI 04:04.0 Multimedia Audio Controller, via Technologies Incorporated ICE 1712 NV24 PCI Multi-Channel I/O Controller, Rev 02. 04:0B.0 Firewire, IEEE 1394 LSI Corporation FW 322/323 TrueFire 1394 A controller, Rev 70. The output of such commands can be tens of lines long, so the previous and next examples contain only the sections of interest. The hexadecimal numbers at the beginning of each line are the unique addresses of the corresponding PCI device. The command LPIC shows more details about a specific device if its address is given with option S, accompanied by the option V. $LPIC S04:02.0 V 04:02.0 Network Controller, Relink Corp RT2561/RT61802.11 GPCI. Subsystem, Linksys WMP54 GV4.1. Flags, Busmaster, Slow DevZL, Latency 32, IRQ 21. Memory at E310000, 32-bit, non-prefetchable, size equals 32K. Capabilities, 40 Power Management version 2. Kernel driver in use, RT61 PCI. The output now shows many more details of the device on address 04:02.0. It is a network controller whose internal name is Relink Corp RT2561/RT61802.11 GPCI. Subsystem is associated with the devices. Brand and model Linksys WMP54 GV4.1 and can be helpful for diagnostic purposes. The kernel module can be identified in the line kernel driver in use, which shows the module RT61 PCI. From all the gathered information, it is correct to assume that 1. The device was identified. 2. A matching kernel module was loaded. 3. The device should be ready for use. Another way to verify which kernel module is in use for the specified device is provided by the option K. Available in more recent versions of LPIC. $LPIC S01:00.0K 01:00.0 VGA compatible controller, NVIDIA Corporation GM107 GeForce GTX 750 Ti, Rev 2. Kernel driver in use, NVIDIA. Kernel modules, Nouveau, NVIDIA_DRM, NVIDIA. For the chosen device, an NVIDIA GPU board, LPIC tells that the module in use is named NVIDIA, at line kernel. Driver in use, NVIDIA, and all corresponding kernel modules are listed in the line kernel modules. Nouveau, NVIDIA_DRM, NVIDIA. Command LSysib is similar to LSPC, but lists USB information exclusively. $LSysib. Bus 001 Device 029, ID 1781:0C9F Multiple vendors US Tiny. Bus 001 Device 028, ID 093A2521 Pizart Imaging Incorporated Optical Mouse. Bus 001 Device 020, ID 1131:1001 Integrated System Solution Corp KYBT100 Bluetooth Adapter. Bus 001 Device 011, ID 04F2:0402 Chickeny Electronics Co., Ltd. Genius Looks Mate i200 Keyboard. Bus 001 Device 007, ID 0424:7800 Standard Microsystems Corp. Bus 001 Device 003, ID 0424:2514 Standard Microsystems Corp. USB 2.0 Hub. Bus 001 Device 002, ID 0424:2514 Standard Microsystems Corp. USB 2.0 Hub. Bus 001 Device 001, ID 1D6B0002 Linux Foundation 2.0 Root Hub. Command LSysib shows the available USB channels and the devices connected to them. As with LSPC, Option V displays more detailed output. A specific device can be selected for inspection by providing its ID to the Option D. $LSysib VD 1781:0C9F. Bus 001 Device 029, ID 1781:0C9F Multiple vendors US Tiny. Device descriptor. B length 18. B descriptor type 1. BCD USB 1.01. B device class 255 vendor specific class. B device subclass 0. B device protocol 0. B max packet size 08. ID vendor 0x1781 multiple vendors. ID product 0x0C9F US Tiny. BCD device 1.04. I manufacturer 0. I product 2 US Tiny. I serial 0. B number configurations 1. With option T, Command LSysib shows the current USB device mappings as a hierarchical tree. $LSysib T /bus 01.port1 dev1 class equals root_hub driver equals dwc_otg/1p 480m _port1 dev2 if 0 class equals hub driver equals hub/4p 480m _port1 dev3 if 0 class equals hub driver equals hub/3p 480m _port2 dev11 if 1 class equals human interface device driver equals USPID 1.5m _port2 dev11 if 0 class equals human interface device driver equals USPID 1.5m _port3 dev20 if 0 class equals wireless driver equals TUSB 12m _port3 dev20 if 1 class equals wireless driver equals TUSB 12m _port3 dev20 if 2 class equals application specific interface driver equals 12m _port1 dev7 if 0 class equals vendor specific class driver equals LAN 78XX 480m _port2 dev28 if 0 class equals human interface device driver equals USPID 1.5m _port3 dev29 if 0, class equals vendor-specific class, driver equals 1.5 m. It is possible that not all devices have corresponding modules associated with them. The communication with certain devices can be handled by the application directly, without the intermediation provided by a module. Nevertheless, there is significant information in the output provided by LPIC. When a matching module exists, its name appears at the end of the line for the device, as in driver equals TUSB. The device class identifies the general category, like human interface device, wireless, vendor-specific class, mass storage, among others. To verify which device is using the module TUSB, present in the previous listing, both bus and dev numbers should be given to the S option of the LPIC command. $LPIC S120 Bus 001 Device 020, ID 1131:1001 Integrated System Solution Corp KYBT 100 Bluetooth Adapter. It is common to have a large set of loaded kernel modules in a standard Linux system at any time. The preferable way to interact with them is to use the commands provided by the kmod package, which is a set of tools to handle common tasks with Linux kernel modules like insert, remove, list check properties, resolve dependencies and aliases. The lsmod command, for example, shows all currently loaded modules. $lsmod module size used by KVM_Intel 138,528 0. KVM 421,021 1 KVM_Intel. ITCO_WDT 13,480 0. ITCO_vendor_support 13,419 1 ITCO_WDT. SND_USB_audio 149,112 2. SND_HDA_codec_Realtek 51,465 1. SND_ICE 1712 75006 3. SND_HDA_Intel 44,075 7. ARC 412608 2. SND_CS 8427 13978 1 SND_ICE 1712. SND_I2C 13828 2 SND_ICE 1712 SND_CS 8427. SND_ICE 17XX_AK4XXX 13128 1 SND_ICE 1712. SND_AK4XXX_ATA 18,487 2 SND_ICE 1712 SND_ICE 17XX_AK4XXX. Microcode 23527 0. SND_USBMD_lib 24845 1 SND_USB_audio. JSPCA_POC 7302 17481 0. JSPCA_main 36226 1 JSPCA_POC 7302. Video dev 132348 tujspka _ mangespka _ POC 7302. RT61 PCI 32326 0. RT2X00 PCI 13083 1 RT61 PCI Media 20841 Video Dev RT2X00 MIO 13322 1 RT61 PCI Hit _DR 12776 0 SND _MPU 401 _UART 13992 1 SND _ICE 1712 RT2X00 lib 67108 3 RT61 PCI RT2X00 PCI RT2X00 MIO SND _ROMIDI 29394 2 SND _USPMID _lib SND _MPU 401 _UAR. The output of commandless mod is divided into 3 columns. Module. Module name. Size. Amount of RAM occupied by the module, in bytes. Used by. Depending modules. Some modules require other modules to work properly, as is the case with modules for audio devices. $ls mod fgrep isnd _hda _intel SND _hda _intel 42658 5 SND _hda _codec 155748 3 SND _hda _codec HDMI SND _hda _codec via SND _hda _intel SND PCM 81999 3 SND _hda _codec HDMI SND _hda _codec SND _hda _intel SND page alloc 13852 2 SND PCM SND hda intel SND 59132 19 SND howdip SND timer SND hda codec HDMI SND hda codec via SND PCM SND sec SND hda codec SND h da Intel SND sec device. The third column, used by, shows the modules that require the module in the first column to properly work. Many modules of the Linux sound architecture, prefixed by SND, are interdependent. When looking for problems during system diagnostics, it may be useful to unload specific modules currently loaded. Command mod probe can be used to both load and to unload kernel modules, to unload a module and its related modules, as long as they are not being used by a running process. Command mod probe R should be used. For example, to unload module SND hda Intel, the module for a HDA Intel audio device, and other modules related to the sound system. #mod probe R SND hda Intel. In addition to loading and unloading kernel modules while the system is running, it is possible to change module parameters when the kernel is being loaded, not so different from passing options to commands. Each module accepts specific parameters, but most times the default values are recommended and extra parameters are not needed. However, in some cases it is necessary to use parameters to change the behavior of a module to work as expected. Using the module name as the only argument, command modeinfo shows a description, the file, the author, the license, the identification, the dependencies, and the available parameters for the given module. Customized parameters for a module can be made persistent by including them in the file /etc/modprobe.conf or in individual files with the extension .conf in the directory /etc/modprobe.d/. Option P will make command modeinfo display all available parameters and ignore the other information. #modeinfo p nouveau. Vram_pushbuff create DMA push buffers in VRAM, int. TV_norm default TV norm. Supported, PAL, PAL-M, PAL-N, PAL-NC, NTSCM, NTSCJ. HD480i, HD480p, HD576i, HD576p, HD720p, HD1080i. Default, PAL. Note ignored for cards with external TV encoders. Sharp. Nofbacell disable FPCAN acceleration, int. FPCAN_BPP FPCAN bits per pixel, default, auto, int. MST enable DisplayPort multi-stream, default, enabled, int. TV_disable TV out detection, int. Ignore ACPI lid status, int. Dual link allow dual link TMDS, default, enabled, int. HMIMITES force the maximum HDMI pixel clock, in megahertz, int. Config option string to pass to driver core, sharp. Debug string to pass to driver core, sharp. NoAccel disable kernel /ABI16 acceleration, int. Mode set enable driver, default, auto, 0 equals disabled, 1 equals enabled, 2 equals headless, int. Atomic expose atomic ioctl, default, disabled, int. Run disable, 0, force enable, 1, Optimus only default, -1, int. The sample output shows all the parameters available for module Nouveau, a kernel module provided by the Nouveau project as an alternative to the proprietary drivers for NVIDIA GPU cards. Option mode set, for example, allows to control whether display resolution and depth will be set in the kernel space rather than user space. Adding options Nouveau mode set equals 0 to the file /etc/modprobe.d/nouveau.conf will disable the mode set kernel feature. If a module is causing problems, the file /etc/modprobe.d/blacklist.conf can be used to block the loading of the module. For example, to prevent the automatic loading of the module Nouveau, the line blacklist Nouveau must be added to the file /etc/modprobe.d/blacklist.conf. This action is required when the proprietary module NVIDIA is installed and the default module Nouveau should be set aside. Note: You can modify the /etc/modprobe.d/blacklist.conf file that already exists on the system by default. However, the preferred method is to create a separate configuration file /etc/modprobe.d/.conf that will contain settings specific only to the given kernel module, information files and device files. The commands lspc, lsysib, and lsmod act as front ends to read hardware information stored by the operating system. This kind of information is kept in special files in the directories /proc and /sys. These directories are mount points to file systems not present in a device partition, but only in RAM space used by the kernel to store runtime configuration and information on running processes. Such file systems are not intended for conventional file storage, so they are called pseudo file systems and only exist while the system is running. The /proc directory contains files with information regarding running processes and hardware resources. Some of the important files in /proc for inspecting hardware are /proc/pinfo lists detailed information about the CPU found by the operating system. /proc/interrupts a list of numbers of the interrupts per I/O device for each CPU. /proc/IO ports lists currently registered input/output port regions in use. /proc/DMA lists the registered DMA, direct memory access, channels in use. Files inside the /sys directory have similar roles to those in /proc. However, the /sys directory has the specific purpose of storing device information and kernel data related to hardware, whilst /proc also contains information about various kernel data structures, including running processes and configuration. Another directory directly related to devices in a standard Linux system is /dev. Every file inside /dev is associated with a system device, particularly storage devices. A legacy IDE hard drive, for example, when connected to the motherboard's first IDE channel, is represented by the file /dev/hda. Every partition in this disk will be identified by /dev/hda1, /dev/hda2 up to the last partition found. Removable devices are handled by the ODEV subsystem, which creates the corresponding devices in /dev. The Linux kernel captures the hardware detection event and passes it to the ODEV process, which then identifies the device and dynamically creates corresponding files in /dev, using predefined rules. In current Linux distributions, ODEV is responsible for the identification and configuration of the devices already present during machine power-up, cold plug detection, and the devices identified while the system is running, hot plug detection. ODEV relies on SYSFS, the pseudo file system for hardware-related information, mounted in /sys. Note: hot plug is the term used to refer to the detection and configuration of a device while the system is running, such as when a USB device is inserted. The Linux kernel has supported hot plug features since version 2.6, allowing most system buses, PCI, USB, etc., to trigger hot plug events when a device is connected or disconnected. As new devices are detected, udev searches for a matching rule in the predefined rules stored in the directory /etc/udev/rules.d/. The most important rules are provided by the distribution, but new ones can be added for specific cases. Storage devices. In Linux, storage devices are generically referred as block devices, because data is read to and from these devices in blocks of buffered data with different sizes and positions. Every block device is identified by a file in the /dev directory, with the name of the file depending on the device type, IDE, SATA, SCSI, etc., and its partitions. CD/DVD and floppy devices, for example, will have their names given accordingly in /dev. A CD/DVD drive connected to the second IDE channel will be identified as /dev/HDC, /dev/HDA and /dev/HDB. Are reserved for the master and slave devices on the first IDE channel, and an old floppy drive will be identified as /dev/FDO, /dev/FD1, etc. From Linux kernel version 2.4 onwards, most storage devices are now identified as if they were SCSI devices, regardless of their hardware type. IDE, SSD, and USB block devices will be prefixed by SD. For IDE disks, the SD prefix will be used, but the third letter will be chosen depending on whether the drive is a master or slave. In the first IDE channel, master will be SDA and slave will be SDB. Partitions are listed numerically. Paths /dev/SDA1, /dev/SDA2, etc. are used for the first and second partitions of the block. Device identified first and /dev/SDB1, /dev/SDB2, etc. used to identify the first and second partitions of the block device identified second. The exception to this pattern occurs with memory cards, SD cards, and NVMe devices, SSD connected to the PCI Express bus. For SD cards, the paths /dev/mmcblk0p1, dev/mmcblk0p2, etc. are used for the first and second partitions of the device identified first and /dev/mmcblk1p1 /dev/mmcblk1p2 etc. used to identify the first and second partitions of the device identified second. NVMe devices receive the prefix NVMe, as in /dev/NVMe0N1p1 and /dev/NVMe0N1p2.